really, but I'll just say yes. Okay. She's at UC Berkeley, and she's going to talk to us about combinatorial optimization and sparse computation for images.
Hi everyone, thanks for having me here. And I apologize if I don't attend the rest of the workshop because it's a very busy week for us. It's a week of PhD exams that I'm in charge of. The work that I'm going to present, I believe, is somewhat unique in that it has machine learning algorithms that are entirely based on combinatorial optimization. And I'll show you, in addition to the theoretical foundation, also empirical studies that indicate certain properties that I think are interesting. So I'll have some standard notation that I'll refer to at some point. So in general, this will be, we'll consider an undirected graph, although all the results apply for directed, but all the applications are undirected. And we have edge weights that are going to represent similarities. The edge weights are going to be referred to as Wij. They are going to be node weights referred to as Qi. Then an important concept is that of a capacity of AB, where A and B are both subset of the set of nodes, not necessarily disjoint. So CAB is the sum of Wij, the weights of the edges, such that one endpoint is in A and the other endpoint is in B. And as I said, A and B don't have to be disjoint. Then DI will refer to the weighted degree of a node, and then degree volume of a set A subset of a nodes, is the sum of DI, and this is a bit of an exercise, arithmetic, which is DA is equal to 2 CAA, the sum of edges inside A, and it's counted twice, plus CAA bar, the edges that go between A and the complement of A. And finally, node volume in terms of the Qi weights will be called Q of A for the set A. So here is an intuitive clustering criterion. And this clustering criterion, I mean, when you talk about clustering, there could be many types of criteria to determine what makes a good cluster. So this is one of them. And it will seek a cluster that combines two different objectives. So one objective is the intrasimilarities inside the cluster. So the cluster is in some sense homogeneous and has large similarity within it. And on the other hand, it is the intersimilarity between the cluster and its complement is low. So the cluster is very dissimilar from the complement. And we have two objectives that could be combined in several different ways. This is one way of combining the objectives. That is, this is also, I'll refer to it as CAT, the sum of similarities between S and S bar. And this is divided by the sum of similarities inside, which is what we want to maximize. And another way, it is a linearization, essentially. The CAT minus some positive lambda times the sum of similarities inside. And this is a slightly different form in which it's to indicate that the weights used for the CAT are not necessarily the same type of weights that are used to measure the similarity within. You are free to use two sets of weights if appropriate. Now the name, why is the name normalized CAT? So the origin is in an article of Shi and Malik that looked at this problem. So if you look at it closely, this is a CAT divided by the weighted degree or the degree volume of the set S, and plus the cut divided by the weighted degree of the set S bar. Some of you may see already that this is closely related to the so-called Chigger constant. And in their article, she and Malik argued that this is a good idea to use it for image segmentation, established the link to the so-called spectral method, that is to find the Fiedler eigenvalue. I'll discuss that. And they included a proof of NP hardness that is based on reduction from partition, which just says that it's weakly NP hard, but it might or might not be possibly strongly NP hard. But this is the proof that they have there that they attribute to Papadimitriou. And it is somewhat misleading because it doesn't capture what really is the difficulty of this problem, which I will address. In a 2007 Nature paper, Sharon et al. Presented this objective, which they call normalized cut, and in fact referred to the She and Malik paper for proof of NP hardness. The subject of this paper was to present a hierarchical aggregate procedure to solve for the eigenvector. So although in theory finding eigenvector is polynomial time solvable, when you get into large images, it's actually pretty intractable. Still polynomial, but you can't really run it. So their algorithm is a sort of hierarchical heuristic of coalescing together pixels, and pixels, the objects and the nodes in this application of image segmentation are pixels. And the question is whether this problem is NP hard, and is it indeed the same problem as this one? So here is a formulation of what I called monotone integer program. So whenever you have an integer program that you can write as follows, it's only a property, the objective function doesn't matter. I mean, here it's a ratio which could be linearized, but the constraints are of the form that each inequality in the constraints can contain at most two variables that appear with opposite coefficients, and the coefficients can be any integer values. They don't have to be ones like it is here. And there could be a constant also. And Zij are variables that appear each in one constraint only and with coefficient 1. So if you have any formulation, if you succeed in writing a formulation of integer program in this form that's called monotone, so the monotone property is that the coefficients are opposite to each other, then you are guaranteed a polynomial time algorithm to solve the problem. And in fact, the polynomial time algorithm, in this case, the variables are all binary, so it is going to be the complexity of a cut on a certain associated graph. In general, it will be a graph, the number of nodes in which depends on the range of the variables. That is, for the variables xi, they will have one node for each possible value. So this presentation, you can say, is not polynomial. Of course, it's not polynomial. It is pseudo-polynomial because it depends on the range, not logarithmically. But this problem also is NP hard when you have ranges. So this was proved by Lagarius to be NP hard, so you can't get rid of it. So in a way, you can't improve on this type of result. this formulation, I didn't write what the variables are. So xi will be 1 if I belongs to the set S, to the cluster we are seeking, and 0 otherwise. And zij will be 1 if one side is in S and the other side is in S bar. And yij is 1 if both I and j are in S. So we can get the objective function written like that, and you can check that these are valid constraints, and this formulation is monotone. So as soon as you write a formulation like that, you can see that the problem is polynomial time solvable. It's not necessarily the best way of writing it. I'll show you how to do it otherwise, but it definitely gives you a recognition of polynomial time solvability. Is there a question about this? Yes?
Isn't this the same as the minimum ratio problem?
It's, if by minimum ratio, ratio cut, you divide by the number of nodes in S.
I guess what I mean by the minimum ratio problem is slightly more general, where the numerator is so modular and the denominator is supermodular. And in Fujishiki, he showed that that can be solved by reducing it to the principal partition problem, where finding a critical value in polynomial time nodes. 95.
This applies to any values of the variables. The variables can...
The original problem. If you take the numerator, which is a non-monotone submodular function, the denominator is a monotone supermodular function.
Okay.
And then the ratio is the ratio of the two. And that's the minimum ratio problem.
Okay. When was this result? 95. Okay, so this was, but as I said, this in 2007, it was presented as an NP-hard problem, this problem. So how do normalized cut and this type of problem compare? So this is again just a little bit of arithmetic. So you can take this objective function and you write the sum of similarities within as half the degree volume of S minus CSS bar, and this is divided by 2. And then you divide both numerator and denominator by the cut, CSS bar, so you get 1 divided by this quantity, which is equivalent, minimizing this is equivalent to maximizing this form, and we just get rid of the 2 and invert it, and it's equivalent to minimizing this form, which is indeed one part of the 2 terms in the normalized cut problem. And I think I'll skip that in the interest of time. So this is how Sharon et al. Showed how to get an approximation solution to the spectral technique. And it would have helped if they were to use the other formulation instead. So I'd like to show you how this objective function of H and C1 and its solution relate to the spectral solution. And I'll generalize it to Q normalized cut, where the weight of each node, instead of being di, the weighted degree, is going to be qi, where qi can be independent of di. And here is some relationship. So there is quite a bit known about it, because the expander problem is this problem, the cut divided by the number of nodes. And here you want, it's essential that you put that the cardinality of S is less than or equal to half of the total. And in fact, the solution, optimal solution to this one, is the bigger of the 2 terms in the solution to this one. So one is within a factor of 2 of the other. Then the Shiger constant that I mentioned is written in this form, where ds has to be for the set S less than or equal to half of the weighted degree of the total. graph, and what we get here is the so-called normalized cut. And this is something I added, this Q of S, and this is related to Q of S and Q of S bar here. So here is a lemma that was shown in a paper, but a special case of this was shown by Shi and Malik, and it's actually a kind of intermediate step for the old results on Shiger constant in the literature going back to the 80s and some of it in the 90s. So you can write this more general form as minimum of Y transpose, and this is the Laplacian matrix. So D is the matrix that has Di on the diagonal. W is the Wij matrix, and multiplied by Y, and then this is Y transpose Q. Q is a diagonal matrix that has Qi on the diagonal. And now there are two constraints here. So one constraint is Y transpose Q1 equal to 0. That is, this is a vector of all ones. And Yi is either minus B or 1. Now, B is something that was never mentioned. I mean, there is no parameter like that. To get an intuition as to what it is, consider the matrix Q to be the identity matrix. So that's a special case. And when it's the identity matrix, so let's say that Yi is 1 if I is in S, and minus B if it is S complement. So then, if you look at this inequality, it says the sum of Yi, the number of nodes in S, minus B times the number of nodes in S bar is equal to 0, and that is equivalent to saying the number of nodes in S divided by the number of nodes in S bar is B. So B is actually the balance ratio between the two sets. Now, you can think of what Shi and Malik were doing. I call this Rayleigh ratio problem. It's related to Rayleigh ratio type of expressions. So essentially what they were doing, or what anyone is doing when considering the spectral solution, is to take a relaxation when you ignore these binary constraints. You just throw them away. And in that case, it's kind of instructive to look at this expression and realizing that the smallest eigenvalue is 0, and that's achieved for the trivial solution of Y equal all ones. So it's the vector of ones. And the reason is that the Laplacian matrix, each row adds up to 0. In this case, also each column. And so that will be the trivial smallest eigenvalue, and the Fiedler eigenvalue is the second smallest eigenvalue. But to guarantee that you get that, this is like orthogonality constraint. So you want a vector that is orthogonal to the vector of ones, which is the trivial eigenvector. Now, the relaxation that I'm looking at removes this equality constraint. And what I want to show you is that this is solved in polynomial time. And by, okay, I think you will believe that. So by a cut on a certain graph. So essentially what we have is, because now we don't have any meaning for B, we are going to solve the problem for any B. It will be parameterized in B. And for any value of B, you can get an optimal solution to either one of the three problems that I posed, like the ratio problem or the linearized problem. So it will be in the complexity of a single minimum cut to solve the problems for all B. And you might ask, how can the solution be presented, because B can take an infinite number of values, but I'll demonstrate that actually you can describe the optimal solution and the output very compactly. So there is a lemma that I don't want to go over all the details, that shows that this Rayleigh ratio is equal to this. So it's 1 plus b squared times the cut divided by qs plus b squared q of s bar. So now as a ratio problem, we can solve it by linearizing it. That is, ask the lambda question. Is there if for given lambda, is the ratio less than lambda? If the answer is yes, then we can presumably do binary search, because that guarantees that the optimal value will be less than lambda, otherwise will be greater than lambda. So we can keep solving this, and this question is equivalent to this question. So we can minimize this expression, and if there is a feasible solution, or certainly the optimum, the minimum is less than 0, then the answer is yes, otherwise the answer is no. So in terms of this Rayleigh ratio, this is the expression, and from the lemma I showed you without proof, this is the same as this expression to ask if this is less than 0. So this is a graph. So there is a general procedure for if you have monotone integer program, how to construct a graph associated with it. And this is the construction in this case. So we get for each node, it has an R coming from the source with capacity lambda qj, and an R going to the sink with capacity lambda b squared times qj. Then there is a node that is selected as sink t prime, and that goes with capacity infinity, and a node that is selected as s prime that also has an arc of capacity infinity. And then in the middle of the graph, we have instead of edges, this is going to be a directed flow. We are going to have two arcs in both directions of capacity 1 plus b squared w ij, between I and j. And now here is a proof that the capacity of a cut in this graph, that a cut that is S union the source and T union the sink, is equal to a constant plus this Rayleigh ratio problem value. So minimizing the cut is equivalent to minimizing that. It's not the same value, but the two get the same solutions. So now there is some process of simplifying the graph. So what I want to show you is that this cut problem can be solved for all values with parametric cut procedure. And in order to show that, I need to simplify the graph. So one simplification is easy. I have, for each node, I have two arcs, and I take the send flow that is the bottleneck, the minimum of the two. So if B is less than 1, I get only arc adjacent to the source, and if B is greater than 1, I get only arc adjacent to the sink. Now, I'm going to scale the arc weights, because here I have in the interior of the graph, I have 1 plus b squared times wij. B is one parameter, and I want to get rid of it. So I'm dividing through separately for b less than 1 and separately for b greater than 1. And I get this instead. So now it's wij, and now I updated the capacity of nodes adjacent to source and sink, depending on whether b is greater than 1 or less than 1. And so the simplified equivalent graph is of this form. So what one should be looking at if you want to apply parametric cut or parametric flow. So parametric flow procedure was first devised by Gallo, Grigoriadis, and Tarjan, specifically with push relabel algorithm. And this is if you have a graph with capacities that depend on a single parameter. Here we have two parameters. Capacities that depend on a single parameter so that source adjacent arcs are monotone non-increasing and sink adjacent arc are monotone non-decreasing, or the other way around, it doesn't matter. But all the interior arcs in the graph, their capacities are independent of the parameter, so they are fixed. Then you can find all breakpoints of the parameter at which the cut is changing, and you find all of that in the complexity of one cut. The result of Gallo, Grigoriadis, and Tarjan had some flaw in that it applied only for linear parameter functions, but there is an easy adjustment, and then it adds, if it's nonlinear rather than linear, then you need to add n log of the range. So indeed, this case, if we choose, so now we'll choose beta, a new parameter that will be a function of both lambda and b. So beta is exactly equal to this if b is less than 1, and equal to this if b is greater than 1. So we have this single parameter and also a linear function. So in this case, the cut problem as a function of beta is parametric, and there are certain properties that make parametric graph easy to solve. So as you increase the source adjacent capacities, you get cuts that are nested. That is, you increase beta, let's say, from some lower bound, let's say 0, so all the source adjacent is 0, so we have an empty source set in the cut, doesn't contain anything other than the source. Then you start increasing it. So for a while you'll increase it and nothing will happen. The value of the cut will change, but still the cut is the empty set. Now at certain point there will be a break point. That is, the function will change and at least one node will be added to the source set. That's called the breakpoint. And then you'll keep increasing it, and again will stay the same, although the value of the cut is changing, but then there will be another breakpoint, etc. So because breakpoints can only be added, you cannot have more than n breakpoints. So you know that a priori that you won't have more than n breakpoint in the graph. And now we can generate for each value of b all the breakpoints. So although the ratio will be achieved at different breakpoints for different b's, but you get all of them, and all that you need for the output is just specify which nodes were added at each breakpoint and what the value of the breakpoint is in terms of beta. And then you have your lambda and you have b that you want, and you can choose what the best ratio is if that's what you're looking for. So let me skip that. So I'll show you a bunch of results, first in the context of image segmentation, which was the original context in which this algorithm was developed. So this image is from the website of Xi that implemented the spectral algorithm of Xi and Malik. And this is the segmentation that you get with their algorithm. So this is the eigenvector result. And it gives a partition, a bipartition, so you can simply plug it in the objective function of normalized cut and see what the value is. And the value is 35 times 10 to the minus 4. Then you write you run the combinatorial algorithm, and although if you look at these two images, it's hard to decide which one is better. This one, if you plug it in the objective function of normalized cut, it gives 1.7 times 10 to the minus 4. This image is presented in the website of SHE, along with the software to demonstrate the work. Now, this is another image that we chose, and we ran it with the algorithm, and look what happens. The sky is split in half with the eigenvector algorithm. The reason is that the software looks for reasonable size segmentation and approximately half the size, and with the eigenvector, it's very easy to get whatever size you want because you essentially sort the elements, the entries of the eigenvector, and you pick however number you want of the largest one. So if you want exactly half, you pick the top half. And this is our segmentation, and this is 127 times 10 to the minus 4 when you plug it into the objective of normalized cut, whereas this one is 1.4 times 10 to the minus 4, approximately factor of 80 better. This is an extensive computational study that was done on lots of images, and it used the weighted degree, which is the way it's usually implemented, and that's the way Shih and Malik algorithm is used, but also we used entropy for node weights instead of weighted degrees. Now, when the bar is longer, the objective function of the spectral algorithm is a lot worse than the objective function of the combinatorial algorithm, and there is actually here logarithmic scale, and this demonstrates how much better it is. And for the entropy, it's even better still. Okay, I want to move on for data mining. So at some point, we started to use this algorithm not only for image segmentation applications, but also in other contexts. So for instance, in denoising spectra of very low resolution nuclear detectors, in ranking drugs according to their effectiveness, and the recent work, there are some other applications in between, but the recent work is in neuroscience. For cell is the neuron cell identification in calcium imaging movies. There is a website called Neurofinder that has benchmark of data sets of such movies, and you submit there, and it runs and ranks the algorithm. So the algorithm is number one in this since January. Now, it can be used as unsupervised or as supervised algorithm. In the context of supervised, we call it SNC for supervised normalized cut, although it's really not related to normalized cut. So we have an extensive comparative study of the technique with general machine learning algorithms. And this work is joined with Philip Baumann. There are two variants that we tested. One is that the node weights are di, that is the sum of the weighted degrees. And the second one, that the node weights are the average label of k nearest neighbor, and we call it SNCK. This is the experimental design. So we did several partitions randomly to different ways, and then we did a fourfold, and I'll skip that. These are the algorithms that we tested. All of them are available, publicly available, and we use the publicly available implementations now. These are This is support vector machine, and this is support vector machine with radial kernel, and that turns out to have certain feature that is different from the others. Now, each one of those have its own parameters that would need tuning. And in fact, we came across the issue very early that when you compare machine learning algorithms that have different number of parameters or different number of values, some of them will be trained more than others, and it's kind of not fair. So in the literature, there was a recommendation rather than grid selection of parameters to do randomized selection of parameter combination. So we did that. I mean, we did earlier also the grid selection, but this time we did that. And also, in order to not prefer one algorithm that has more parameters to another, we gave a time limit for the tuning. So all of them had the same opportunity to tune the parameters. And these are, I mean, there are lots of details here. Basically, the boldface are the best algorithms. And there are lots of data sets here. The largest ones here are 20,000, but most of them are size of 1,000 or so. And also, our algorithm is actually a classification algorithm. It's binary classification. So in many of these data sets, there are positive and negative classifications. So that's easy. It becomes binary. In some of them, it's not. And then we chose the first value, just arbitrarily, as number 1. So when we have F1 score, some algorithms can, like, this one gave value 0, and that was the reason. So the results, if we take average, and average is not right, but it's pretty hard to go through the details of every entry in the table. But so if you do take average across these data sets, then SNC was best in terms of, so this is a percentage of performance compared to 100%. So this is 77.5. Now another aspect that is of importance is that some algorithms can give good results occasionally, but bad results also occasionally. So they are not robust. So to capture robustness, we also took the minimum entry. So a lot of these have minimum of 0, and SNC was also best in terms of the minimum. So the minimum indicates some kind of robustness. You never do on this data set worse than 23%.
Question?
Yes.
Neural nets, I mean, that's the inevitable question. Do they work on these data sets?
Actually, neural net is very disappointing.
Where is that?
This is the first one, artificial neural network here. So we ran against it also. So in these experiments, I mean, the 64.9% is not bad. The minimum is 0. And the performance is not good. And this has been consistent in many empirical studies that we did. But from what I know of neural networks, it has the capability of doing learning and observing lots of scenarios over time, which the algorithm I presented does not. And as such, it could work really well for certain contexts. We actually tested it even with deep learning, even on the digits data sets. It did not work well.
On digits?
Yes, on the one that Hinton presented as, in fact, my students spent a summer at IBM, and they had a group trying to replicate these results, and they were unsuccessful.
No, that's on digits?
Yeah, on digits.
I think many people here would be very
What is
surprised.
the
goal in digits to, as far as
To recognize digits. But that was,
99.9 or something now, right, with these neural nets?
that's not what they got when they tried to implement it. So I don't know what kind of training
What did you
went.
get?
Huh?
What did you get with digits?
I did not run it. My student ran it with a group at IBM.
Yes.
I don't know exactly, I cannot quote the numbers, but they didn't get anything similar to that.
Is this MNIST you're talking about? The
Yes.
So-
Has anyone here implemented that and run it? Yeah, and it ran very well?
Yeah.
Okay.
there's a little demo in Bopaweb, an open source, open learning system that I work on, where you could just type make and it'll get you down to about a 1% error rate.
Okay, yeah. So they were not able to replicate it. I should ask again what exactly they did, but by the end of the summer they were not able to do that. So maybe they did more than just this data set.
For MNIST, you don't even need GPUs or anything. I mean, for MNIST, you can do it on a laptop. Don't need any GPUs or anything.
Right.
So is there a reference code for H&C?
Yes, there are several references at the end of
Not
the.
references, reference code.
Yes, there is a reference code. Yes.
I looked at your website, I didn't see it there. Is it on here?
Yes, it is, although I'm not sure the parametric version, I'm not sure that we released it already. I have also in GitHub, we have a code that is released. If you send me email, I'll give you the references for that. And then we did study of the ranking. So the rank, one corresponds to highest rank, to second highest, etc. So the smaller the number is better. And again, SNC came out good. Then standard deviation across the randomized splits, just to show that there was no overfitting. Everything is consistent here. And the evaluation times, this is once we set the parameters, these are the running time of the algorithms. So SVM is in fact a very good algorithm, but it can take an enormous amount of time to run. Also, what we found out that the tuning time. So tuning time, they are almost all very close because we put a limit on that. And what our conclusion is that the top ranking algorithm are all of these at the end here, that all of them are using pairwise similarities. And in fact, it has been observed by others that pairwise similarities are very good to use with machine learning. So they might be very good to use, but unlike image segmentation, where we use pairwise similarities of a pixel with its neighbor, so the degree is small, when you have data set, anything can be a neighbor of anything else, and therefore you have quadratic growth in the size, and you can't really run it. So that was the next step, and this is where this sparse computation goes in. So normally we get, if you're going to make all pairwise similarities, it will go quadratically with the size of the data set. And we cannot afford to do that. And so we are looking for some kind of sparsification, but not in the normal sense. So the normal sense is that you are given, say, a matrix of values, and you decide how to essentially round down to zero part of it to make the matrix sparse and to maintain certain properties. But for this to work, we need to have the matrix in the first place, and we don't have the matrix. In fact, we don't want to compute it in the first place. So the idea is to be able to detect where are the relevant similarities without computing them. So the idea that we are using is, I call it approximate PCA, but it's essentially based on the constant time SVD of the Rinius, Cannon, and Mahoney algorithm. And some of you may say, why don't we use the localized hashing that can have similar properties? But we implemented that empirically, and this worked a whole lot better than localized hashing. So what's the idea? The idea is to project the space on the, say, 3 leading eigen vectors or principal components, and then subdivide each dimension by a parameter k. So the larger the value of the parameter, the smaller is the resolution that we are going to get, or finer resolution. And then in 3 dimensions, we get a bunch of blocks. And taking a block here, we are going to compute the similarities between everything that falls in the same block and its neighbors, so in this case, 26 blocks that are neighbors. And although there could be errors, I mean, there could be an error that a relevant similarity is not computed and is 0, or that irrelevant similarity is computed. The latter is not important, so we wasted computation. But the first one, we found that even if we miss it, it doesn't make a difference. And I'll show you empirical results on that. I'll skip that again in the interest of time. So here we are testing larger data sets. And these are the number of objects, so 20,000, 45,000, and 581,000. And so what we did was the orange line is we computed the entire matrix. So for all of these data sets, we were able to compute the entire matrix. And then we applied this sparse computation by, as we increase the value of k, the finer the resolution, the density, this curve shows the density of the matrix. So it goes exponentially to become very small. And then we computed the accuracy of the algorithm as it changes with the resolution. Now, this right-hand side axis is showing you the accuracy. And as you see, it is worse here and here, but this is a small fraction of a percentage. Here also, it's less than 0.5%. Also here, and in this case, it's a little bit higher. So we found that it's almost not worth it to have the complete matrix because we get the same results without the complete matrix, with very sparse matrix. Now the larger one is 580-some thousand, and we couldn't compute the complete matrix, so we started by subdividing to 100, and we got a certain density, and then subdividing to 500, and the density has gone down. And we computed how the accuracy is changing, and in this case, it has gone up. In any case, the accuracy does not change very much, and often it can go up. And the reason why it could go up is that having a lot of small entries in the matrix can actually result from error and noise, and this has an effect of cleaning it up. So in this case, we got accuracy of 89.72 with 0.008% of density, where the complete similarity matrix would contain over 54 billion entries. We scaled this up to data sets of size 10 million. So here are a bunch of references on the various things that I mentioned. And I'll be happy to take questions.
You can set it.
So please send me email if you want access to the codes. So thank you.